So just a recap of the salesperson problem. I really like this because it sums everything up. And I really like, now that I think I understand it totally after this weekend, couple of quick things. When we did the postperson problem, what did we have to do that we don't have to do this time? All the edges. So something like this, you would have to cover all the edges for the postperson problem. And we looked for odds. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 4. So all these are even. So is this going to be a problem for us with the postman problem? No, because all we have to do is go around, zigzag the star, and we'll be back. If all of the vertices are even, it's no problem. But as soon as you have something like this, and you have some odds, and I'm going to do this here. Did I do that right? 1, 2, 3, 4. Yeah. So which ones are odd? If we label them A, B, C, D, E, which ones are odd? A and B are odd. So what you're going to have to do there is you're going to go around this whole thing. You're going to do this, but then what are you going to have to do? Repeat AB. And you only have to repeat once because there's only 2 odd ones. The more odd ones, then you're going to have to be a little more strategic. So that was the postperson problem, all the edges. Now what's different here is that we don't have to worry about all the edges this time. All we have to do is worry about the vertices. So this one, you know, a little easy. All you have to do is go around like that and you get to all the vertices and you're back. But maybe there's a shorter route. And so when we look at weights, there definitely may be a shorter route. So with this one, all vertices. And is it okay to hit a vertice more than once? It is, especially you'll have to if you're coming back to the beginning. But more than likely, to minimize, you may have to go through. And so that's where we got the difference between these two, the classical and the practical. The classical is that if it's a complete Hamiltonian graph, all of those are going to be hit once except for the first one. And then for the practical, maybe you'll hit one of those more than once to get a minimum. So our goal is to get the minimum weight, not necessarily to only hit them once. Does that make sense? Okay. Here's the part that didn't make sense to me before. I get it now. And that is that a weighted complete graph is Euclidean if there aren't any cases where you have 3 points, V, U, W, U, V, and W. And I'm just going to make these here. U, V, W. And if this is 1, this is 2, this is 5, okay, what's the best? Well, actually, that wouldn't be the one I want. I would want to go something like this. I would go 4, 2, and 5. So going from U to connect these, are you going to want to go U, this was a V, W, and then back here? Or do you want to double up on 4, 2? Do you want to go U, V, W, then back to V and back to U? Which is the least for those? Do we want to do a circle or a cycle, or do we want to double back? Cycle. But what if this was an 8? Now what are you going to want to do? Double back. So Euclidean means that the triple here, there's no need to double back with any 3. So all of these is that this one here is less than 4 plus 2. This one, we'll just call it A, is less than the 4 plus 2. So maybe it's 3, maybe it's 5, maybe it's 5.5, but to be Euclidean, you don't go doubling back. Now here's what's confusing. Here's Euclidean, and then the paths we take are what? Hamiltonian. So this terminology gets a little confusing. Euclidean just refers to the fact that we don't double back. So if you want to, you can say don't double back on any triples. Any triples of points. They call it triangle equality. Does it make sense now? Yeah. And that's true too. But weights don't have to be lengths. They could be time or cost. But I like that idea, is what they mean by triangle equality is if it's a triangle, this has to be less than the sum of those two. Great visual. That's super helpful. Okay, so then we get into these techniques, and I know that was a part that was a little confusing last time. There's 3 techniques you need to know. The upper bound, the nearest neighbor, and the deleted vertex. Those are the 3. Do you want to do the easy one first? I do. Let's do the upper bound. I love the upper bound. The upper bound is simple. You just make a minimum spanning tree and double it. Think of doing that minimum spanning tree and then just coming back the same way. There's your upper bound. It's lame. You'll be able to easily find quicker ways, but that's a fast way to find an upper bound, which I think is a very helpful thing. So you just make your minimum spanning tree, and they put a little boundary on this to use Kruskal's algorithm to find it. I thought that they had G was Euclidean. Yeah, G is Euclidean. So let's think triangle. Think of Moose's triangle. All right, let's do the last one next. I want to do the last one next, the deleted vertex. I think this is the next easiest one. This is one of the minimums. There's 2 minimums. One is the deleted vertex algorithm, and the other is nearest neighbor. The deleted vertex algorithm is you take out a vertex. Now here's the sad part. Any vertex. So if it's any vertex, you might have to take out all of them one at a time. That's what's lame about this one. Now on a test, if they say using this vertex, you go, good, I only have to do that one. But it's still a good idea. Find a minimum spanning tree on the remaining graph, and then on the last 2, connect with least weight 2 edges. It's a really poor sentence, but so you take out a vertex and you find the minimum spanning tree of what's left, and then from the 2 least legs that are left, you should be able to complete that cycle. And note that it has to make the cycle. You might have to, certain ones you might have to adjust to that. So let's do one here. Apply the deleted vertex by deleting A. Oh, I love it when they tell us which ones to delete. So we're going to do it. We're going to delete this one. This is off the table. Okay? So now we're going to find the minimum spanning tree of those that'll connect B, C, D, and E. So which is the least of those to start with? The 4, ED. So connect those. Now we need to connect B and we need to connect C. What's going to be the least to connect B and C? 6 and 7. Yeah, the 7 here And then you could do either of these 6s, right? Either one will satisfy this. Let's do this one, see what happens. Okay. Now, do we have a least spanning tree? Minimum spanning tree? Yes. With this as an option if we have to. Okay. So now take a look at what's left. You have, for the A, you have the 7, the 8, and the 10, and the 5. Okay. Now we want to complete this to make a complete cycle. And to do that, which tool should we use? For sure we want to use 5, right? For sure you want to use 5. Ugh. There's 5. And then to make the cycle, what are you going to do? 7 or 8? 7? Yeah, because then you can go here. Oh, this B is stranded, isn't it? So maybe what we want to do, this is hard to see for me. Maybe what we want to do is we want to go here, 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 here. Let's see, wait a minute. D. You have to complete the Hamiltonian cycle for these, and then you can get what those are. Then the last one, and I skipped it because I think that those tie together real well, is the nearest neighbor algorithm. This is one that is kind of the most obvious. Start with a vertice only of a weighted complete graph. So we start with any given point. Start with A, for example. And then once you've seen that, just mark it as visited. Find the edge of least weight that connects to it. And then once you get those, just circle them or draw the line, and then go until all of those vertices are given. Now you're going to, once you get to the end, you're going to visit all the vertices. Then you have to go back to the beginning to finish it. So for something like this, find a minimum spanning tree. This would be my minimum spanning tree. And then in order to do the nearest neighbor, we got to do a problem like this. You start with one of these minimum spanning trees here, 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 and probably here. Okay, that's the minimum spanning tree. If we do nearest neighbor and we start with A, nearest neighbor would probably be here. And then from C, where are we going to go? D or B? Or E. Yeah, we're going to do E, don't we? Okay, and then where do we want to go? D, and then we can either go to A or go to B. Which do we want to go to? B, and then we've hit all of those, right? So now we have to go back to A, and so that completes that Hamiltonian cycle and gets to all the vertices. So that's the nearest neighbor. So nearest neighbor, probably a nice way of doing the minimum. Going back, the first thing we did was the upper bound. I'll ask you on a test, find the upper bound, do the minimum spanning tree, double it. That's your upper bound. Then try the nearest neighbor, and then try the delete a vertex. We're going to do a couple here. Yeah? Go to number 2. It says find a minimum spanning tree for the given graph, hence find the upper bound for the traveling salesperson problem. So here we go. Which is the minimum spanning tree? Tell me 2 vertices to connect. SP, then what? Go to Q, PQ, and then definitely where? QR. So for part A, you're going to go PQ, SPQR, and then you're going to go back to QPS. Now that obviously that's not the best way but it is the 2 times 32 plus 55 plus 43. It helps to at least get some visuals on this. So this is going to be, what is this? 98, 130 times 2 is 260. That's going to be my upper bound for sure. By deleting each vertex in turn, use the deleted vertex algorithm to find a set of lower bounds. So let's delete P, Q, S, and R. Oh, we haven't done B yet. Thank you. For B, what you're going to do is complete the tree and hence find a better upper bound. So instead of going S, P, Q, R, and then back, what should we do? Just go to S there. So this is just going to be 32 plus 55 plus 43 plus 86. That's going to be better. It's going to be 130, or is it 216? Yeah, I'd say that's a lot better, isn't it? Let's remove P and do the vertex one. So removing P, we just have to connect S, Q, and R. How are you going to do that? You're going to remove P. What are going to be the 3 you're going to want to use? Yes, you're going to want to do RQS. So that's going to be 84 plus 43. Okay. Now you're going to need to complete the cycle. So now you're going to do the 2 that are least from there, which are going to be what? Now you do have to make a cycle. Oh, wait a minute. Are you right? Find the minimum spanning tree, add to the length the minimum spanning tree of the 2 shortest, the lower bound minimum weight of the solution. You need add to the lengths of the 2 shortest deleted edges. Oh, okay. Okay.
It doesn't give you an actual answer.
All right. Okay. So good. So then this is going to be what is it? 32 and 55. So this is going to be 127 plus 87, which is, what is that, 114? Or 214? 214. But like I say, that isn't actually going to work. That isn't going to make it. Let's try another one. Go ahead and try another one. Try the try removing Q. It's going to be 32 plus 65. And then the ones that are left, shortest for Q, are 55 and 43. And so this is going to be 97 and 98. What's 97 and 98? What's that? 197, yeah. Okay. And then go ahead and you can do S and R there. Use the nearest neighbor algorithm starting at P to find an upper bound for TSP. So we're going to start with P here, and we're going to use the nearest neighbor algorithm starting at P, find an upper bound. Okay, so nearest, what's the shortest of these? 32. Okay, shortest of 84 and 86? 84, and then we need to get to the remaining vertice, and then we need to come home. So the nearest neighbor for that one is going to be 32 plus 86, 43. Did I do that right? Not 86. Try again. 32 plus 84 plus 43 plus 65. So this is going to be 108. And this is this 214 again? Okay. So this is going to be 116, 214. Is it 228? 224. That's right. All right, so we've lowered this maximum now. It's somewhere between 224 and one of these. And so then we want to solve them. So going back here to this vertex one, what's different is you're trying to get the largest of these because the largest is going to reveal the minimum, which seems counterintuitive, but as we said, these aren't going to be real. At 197, you can't get there because it doesn't make a Hamiltonian. But the largest of these will be your minimum. And so in this case, I think it's 214. M's going to be greater than 214. That's going to be my minimum. So I've got my maximum of 260, my minimum of 214, and then you just kind of work at these. 224, that's pretty good. And if you just keep looking for that range. I would spin off of one of these or one of these to get that. And I would guess you're going to be doing this one and this one because they're so much smaller. And it's probably RP. I don't think there's any way of connecting these that's going to be better than this one. And so that's just going to be 55, 32, 43, 86. So 7 and 9 is 16, 8 and 8, 16, 21. 216 is their least. Yep. And you know that makes sense. It's between 214 and 260.